the next major factor that plays a role in drifts in the link, and that is polarization drift. This can degrade quantum communication, like we saw earlier, in terms of both affecting the quality of the entangled state that reaches the end node, as well as the a metric that is often used for key distribution called quantum bit error rate. There are two major approaches that are often seen in compensating for polarization drifts, one being classical reference based or quantum signal based, like we similar to how we discussed for timing synchronization. In the case of the classical optical signal that is sent alongside the quantum channel, it allows for fast drift correction, has similar trade-offs like we talked about earlier, and would require dedicated hardware like polarimeters. And uh, the case of quantum signal based correction uh, would help in reducing the hardware requirements, but the requirement would mostly be on the rate at which the photons are generated. And so, based on whether the rapid drifts occur in the system, or you want to opt for a simpler and approach, it would help to pick between the classical reference approach or the quantum signal based approach here as well. Let's see some examples here to understand some of the approaches that relied on the quantum bit error rate metric that is used in quantum key distribution to study the differences between the keys that have been obtained by the two end nodes. And this helps as a feedback metric for determining how much drift should be compensated for in the link. And that could be used in an optimization routine as well. So here in the first example that we are looking at, the study was conducted in Singapore, and it used a 10-kilometer underground link in a loop configuration. The polarization compensation used the quantum bit error rate signal that was obtained, and this was done through blind search algorithm. That is, the bit error rate was used as a feedback, and a search algorithm determines what should be the changes that need to be applied on the polarization controller so that optimal correction can be achieved. And in this particular example, it took about 10 to 20 minutes to achieve a correction. Let's see another example for a longer link distance going about 200 kilometer between the two end nodes. We've seen this example earlier as well in the case of timing drifts. The source node here was located in Vienna, and the end nodes were in St. Polten and Bratislava. In this example, the polarization compensation took a significant portion of the total operational time, which is close to 25%. So the compensation in this case was only triggered when the QBER exceeded a threshold. And a QBER threshold is something that's popular in error correction of these key distribution protocols, because it depends on whether the protocol is running within a particular threshold. You can achieve error correction as well as authentication and maintain positive key rate at the end of the protocol. So once the QBER exceeded a threshold of 9% in this case, the compensation routine was triggered, and it was used to reduce the QBER metric and bring it down to acceptable regime again. And this relied specifically on hill climb algorithm. What we see here is these examples highlight that the choice of compensation strategy affects how long the system has to dedicate to key generation versus stabilization, and this is largely dependent on the link losses, link distance, and the pair generation rate. And based on that, a choice of hardware controllers and the approach that should be used for compensation should be decided. Let's also see some examples next where classical reference was used for polarization compensation. And in this particular example, the experiment was conducted in a laboratory setting, but there was a 25-kilometer spool that was used. What you see here in the red box represents the polarization compensation hardware. Here you'll observe that there is a switch that is used to either pick between the quantum signal or the classical reference that is used for polarization compensation. The reference is at the same wavelength band as the quantum signal. So, this is an example where time multiplexing was used. Uh, what is done is either the quantum signal or the reference signal is routed to the fiber link. When the reference signal is routed, it majorly comprises of two polarization references that are subsequently sent. And at the end node, uh, there is another option to route the classical signal to a polarimeter, which determines the transformation that has occurred through the fiber link. And this helps in determining what is the Stokes parameter, what is the unitary transformation that has occurred, and what is the correction that needs to be applied on the end node polarization controllers to compensate for the link. So you can see here in the figures shown below, there are examples where in the presence of the polarization compensation versus absence, there is a significant difference in the measured visibility. It is very much stable with polarization control despite huge temperature fluctuations. And in the former plot, there is a degradation in the visibility over time when there is absence of compensation. I also want to talk about another work that was conducted by a startup QNect and deployed in New York City. This was a work that involved 34 kilometer of buried fiber in New York City. And in this case, time multiplexed polarization references were used. There is a polarizer and a polarization controller, and there's a switching mechanism like we described saw in the previous case as well, that either allows for the quantum signal or the classical signal to pass through. And at the end node, a polarimeter makes measurements of the classical signal and helps determine what is the transformation that needs to be done based on gradient descent algorithm. So we see here that for polarization drifts, oftentimes the references are picked to be in the same wavelength band, so that this helps determine the transformation that occurred in the quantum signal to be mimicked in the classical signal as well. Huge wavelength difference between the classical reference and the quantum signal can lead to different drifts in both these wavelength bands, and that is something that needs to be studied in addition in order to make for compensation if the classical reference is at a very different wavelength band. However, this is also being explored.